All right, so now it's time to begin. Latifah came up and asked about the session ID. Here's the session ID right here, WEBB ASTR, capital W, and then capital ASTR, for those of you who are using the ResponseWare software. If you're using a clicker, then it's channel 33. So today is going to be the first day when we're going to actually have this counting for grades. And if most people answer correctly, I will just go to randomly picking one of these 12 cards. I'm conveniently using my business cards. I've had them for 13 years and I've used about 40, so I figure this will be a good use for them. I will go through and randomly choose a card, and then that person will be asked to explain their answer. And you'll be graded on your quality of your explanation, even if it's the wrong explanation, just to show the thoughtfulness and whatnot. Aldwin. Honestly, I don't remember the order. So I can't answer because I don't remember the answer. I don't remember where I have things set up. Sorry.
So what you're saying, Dr. Evans, you're playing me. I get it.
What I'm saying, I have two questions, and so if you miss one, it's going to hurt, but I don't remember where they are. I know what they are. All right. Okay, so we're going to learn today about eclipses and calendars. This is actually the second part of the lecture I started on Friday. So, hey, good you didn't leave now because we start off with a clicker question. So, but goodness sake, that's where I want to be. Okay, you can start answering now because it took me that long to get set up. And since we have a small class, I'll tell you who hasn't answered yet, just in case you're, think you've answered and you haven't. So the people who I don't have an answer yet from are Hannah and, now Hannah, so just Jessica. There we go. Oh, and is this Russell?
Yes.
All right. So question, you're probably not going to get it in time. I'll just move on. Okay, so the answers that we had here were, 2 people said 365 days, 7 said 365.2422, and 1 said 365.25. Now, we've had this question before, so this was a review, and we had, it doesn't really do any good to ask you to defend your answer because it's going to be what I remembered for everybody, right? So I won't go ahead and ask anyone to defend this answer, but when I talked about this, I made a reasonably big deal for the very last thing in class on Friday, that the reason we have our convoluted leap year system, it's not just adding a leap day every 4 years, but also skipping a leap day every 100 years, but adding it back in every 400 years, is to get to an average of 365.2425. That's what our average is with that system. Remember I talked about you have a homework problem that has you try to come up with a leap year system that would match, I think it's 365.170 days a year. And so you'll need to go through and think about what fraction gets you close and then how you can add and subtract to get up to that. Of course, why is our day that long? It's just the Earth's rotation. It's not like we have any there's a reason for it. It's just the Earth's rotation. So now, why is the sidereal day shorter than the mean solar day? We've talked about that. I did my little example spinning around here. We even had a question on the last quiz about it. It's because the Earth is rotating in the same direction that it's orbiting around the sun. And because of that rotation, you actually have to do slightly more than one rotation to get, or because of the orbit, you have to do slightly more than one rotation per mean solar day. In fact, as you go around, and you can count this, let's just do it real easy like. I will have my 2 students in the front. So, Russell, you count the number of times that my face points to this right here. And Hannah, you count the number of times that my face points to you. So we're starting at 0. Well, actually, let me reverse that because right now Russell is right in front of me. Russell, you're going to count the number of times I look at you. Hannah, you're going to count the number of times I look at this.
Okay.
So I'm looking at both of them right now.
Okay.
So we start at 0, and we go around, and just to make it easy now, it's 1 for Russell, but still 0 for him.
Yeah.
So I keep going.
1.
This is so fun. Y'all wish you could be up here doing this. Okay, how many times did I look at you, Russell? 6. How many times did I look at that?
5.
Okay, that's the way it should have come out. They both can count. Good job. Okay, so what we had was the number of times that I looked at Russell, which was the number of complete rotations I did, was 1 more than the number of times I looked at the sun, the thing on the table. And that's always the way it's going to be if you're spinning the same direction. So that means that in the time that the Earth looks at the sun, one place on Earth looks at the sun 365.2422 times 1 year, the Earth will have done, as seen by the stars, 1 more rotation, so 366.2422 sidereal days. Sidereal is with respect to the stars. So it's just a difference of 1, which allows us to use very simple math to find out how long the sidereal day is. We know the mean solar day is 24 hours. And because 1 year is 365.2422 mean solar days and 366.2422 sidereal days, we just take that fraction and multiply it by the 24 hours per mean solar day, and we come up with a sidereal day is 23 hours, 23 hours, 56 minutes, and 4 seconds long. And so that's the amount of time it takes for the Earth to do 1 rotation, as in 360 degrees. The 24 hours is a little bit more. And so we talked about right ascension and declination. Declination was the angle north or south of the celestial equator that we use for identifying stars on the celestial sphere. Right ascension is the angle from the prime meridian of the sky to a location. It's equivalent to longitude on Earth, but because of the Earth's rotation, we measure that angle in units of hours, minutes, and seconds. Right ascension, stars rise in hours, minutes, and seconds. And for 1 complete rotation, you have 23 hours, 56 minutes, and 4 seconds. That's all you have on the celestial sphere because it's representing 1 rotation, not 1 mean solar day. Any questions here? Because this can be confusing. We're all good? Okay. Now, this slide here doesn't really have anything new. I talked about all of this last class period, so I'm going to zip by unless anyone wants to ask a specific question about the tilt and how that affects the Arctic Circle and how long we have sunlight. Going by. Time zones. We live in a world with many time zones. Time zones are there because local noon is different for every place on Earth almost. You go around and you change your longitude and you're going to change the time that's local noon. And so what we've done as a society is we said, okay, let's take this band here that is roughly 1/24th of the circumference of the Earth, and let's say these people are all in the same zone, so they'll agree, they'll look at the clock and they'll say, yeah, it's the same time. And noon should come around when the sun is overhead in that region. And then we go over and the next one, each one has its own time zone, so that in each time zone, noon should be roughly, the hour should be roughly sometime the sun is going to pass overhead. Right? That's why we have those time zones. Now, if you're doing things on computers, or if you're in the military, something like that, you might use a Zulu time or a Greenwich Mean Time. There are different names for it. Universal Time, UT. which is the time in Greenwich, England, or it says there UK. That gives you a time that you can always compare without worrying about time zone. But we kind of like the idea the sun rises somewhere at 6-ish in the morning, sets somewhere 6-ish in the evening, and is overhead at noon. And so with our local time zones, we have something of that nature. Whereas if you're to use the Greenwich Mean Time, everybody can agree on the Greenwich Mean Time, but you can't say, oh, well, at 0400 hours, the sun should be coming up in 2 hours, because it just depends on where you are in the world if you're using the universal time. Now, if you look at these time zones, you see the prime meridian. The prime meridian here is going through Greenwich, England. Okay, I did not hit that very accurately, but at the same time, how do I know where Greenwich is? It's somewhere in this vicinity, but I'm not a cartologist or Mr. Geography. I do know that my ancestors were from here and from here and from here. Oh yeah, and some of them down here. We have these time zones. The prime meridian is where we measure latitudes from. And that's where we measure our universal time from. And then we have those time zones going plus to the right, minus to the left. And so to get the local time, we can look where we are. And we are here in this time zone. So if we take -6 from the universal time, that will give us our local time. And these lines aren't just straight lines. You see Greenland here has its own time zone pretty much for the entire island, even though it stretches across what should be 3 different time zones. Now, it looks like Greenland is really, or Iceland. Yeah. That's
Iceland is the small one next to it.
Okay. Yes, once again, me, geography. It's not my profession. So it looks really big, right? It's not really that big, because the Earth is, I belong to a creationist Facebook group, and there are people in there constantly harping on the Earth being flat. It's so demonstrable that the Earth is not flat. Like, look at the shape of the shadow the Earth casts on the moon. Or when you go up in an airplane, look at the curvature. You can see it. But they deny it. The truth is, because the Bible has things like, as far as the east is from the west, or the angels went to the 4 corners of the earth. And so people say, okay, the Bible says there's 4 corners of the earth. Then by golly, the earth is flat with 4 corners. Because God said it is. And, I tend to think the 4 corners of the earth is a figurative term meaning everywhere. Not a literal term meaning we laid out the flat earth and we found the 4 corners. But that's the why. Okay, so assuming that you buy into the earth being a ball, by the way, they have a catchphrase. No curve, no ball, game over. Anyway, assuming you buy into that, then it's pretty easy to understand that we make our maps flat. But the Earth's surface is not flat. And so you have to change the scale as you go across the map. So if you're at the equator, the Earth has the biggest circumference of the equator. So things that are big that are at the equator look small. Things that are close to the poles that are small look big because of that squeezing. So that's actually not a very big island overall. But it looks huge because of how we make our maps. So how do you get a real idea of how big it is? Look at a globe. The globe will give you the correct sizes. There are some people who take this and put it into a big conspiracy that the Eurocentric world is in it to make Europe look bigger and other countries look smaller. No. It's just a way of trying to draw something that doesn't really fit. And so this is the standard way we draw. I think it's called the Mercator way of drawing it. I didn't mean to make it that small. Also notice some other interesting things, like out here we have a very interesting intrusion on the time zones. And in fact, in that region, I think it's like where Samoa and Tonga are, we have an interesting situation. The international date line comes between like these islands. And so this island is Sabbath and this island is Sunday at the same time. And so what do you do if you are Seventh-day Adventist? You keep Sabbath. I'm here, it's today. I'm here, it's yesterday. And so that's one place on earth where Seventh-day Adventists keep the same day as Baptists. Because they said, okay, look, we're going to find a time and consider this Sabbath both sides of the date line. And so on one side, on their calendar, it's keeping Sunday, and the other side of the calendar is keeping Sabbath. It's an interesting, way of trying to come to sense when you have, I thought about this when I was a kid. We keep the Sabbath from sundown to sundown, which is really easy, but when you start traveling, it messes things up. In college, we were in Japan, and the sunset required tour. So the sunset, so sundown Friday night, it was Sabbath. Then we got on the airplane an hour later, and we arrived in Hawaii Friday morning. If you are a legalistic Seventh-day Adventist, what are you going to do? The legalist would say, well, we'll keep from sundown Friday night until we cross the international date line. And then it'll be back a day, and then we'll keep again. We decided that really didn't make sense, so we would just consider we'd be at Sabbath the entire day in Hawaii, so we would just follow that, trying to be more reasonable about how you deal with that. Of course, another cool thing is on my first wedding anniversary, we flew from Malaysia to the United States. My wedding anniversary lasted 30 hours. That was kind of cool. Okay, so, did I point out the international date line is 12 hours removed from the prime meridian? It's on the opposite side of the Earth. If not, now I have. Okay, lunar cycles. So we have the Earth's cycles around the sun, which we measure off from that, the mean solar day, the time from when the sun's overhead to when the sun's overhead, and the year, the time for us to do a complete orbit. Now we're going to go to the moon. The moon, like the Earth goes around the sun, the moon goes around the Earth. And so as the moon goes around, it takes 29.5 days for, and I have there the sidereal month. I swear that's the synodic month rather than the sidereal month. I think I have that wrong. Anybody want to go ahead and look that up, like on your smartphone? I could have it right here, but it just feels wrong. It feels like that should be the synodic month. What's the difference in the synodic month and the sidereal month?
The sidereal month is the time it takes the moon to orbit once around the Earth with respect to the stars, approximately 27.
That's what I thought. This is the wrong one. This is the synodic. I went through before class and highlighted it and didn't notice it said sidereal. So what is the sidereal?
The time it takes the moon to orbit once around the Earth with respect to the stars, approximately 27 and 1/4 days.
Okay. I round to 27.3 days. That's what we usually do. So the sidereal is actually 27.3 days. Please excuse my error there. The synodic is from full moon to full moon. So the synodic day, or month, is analogous to the mean solar day. From full moon to full moon as measured from Earth. And the sidereal is the time for the moon to do one orbit around the Earth. Now the moon is in a very special kind of orbit. Here's what the moon does. So we'll have you two count the same. It'll be really boring. So here's what the moon does. You guys ready to count?
Yeah.
So every time I look at Russell, he counts. Every time I look at that, you count. So here we go. Okay. Because the spacing. I got it. Okay.
Always there.
I was always looking at this. So it actually is 0 for Hannah's count because I never looked away from this, but 1 for Russell's. Russell's count was still 1 higher, but hers was 0. What's going on here? Well, it does rotate because it did 1 rotation as I did 1 orbit. We say that it's tidally locked. Okay, you guys know about tides, high tide, low tide. Well, tidal forces is a term for the fact that, and the high tide, low tide are caused by the same thing we'll talk about later. Gravitational force is the force that is holding these things together. And gravitational force is stronger on closer objects than it is on farther objects. And so right now I'm attracting Russell, I'm attracting Max. But Russell is closer, so I'm attracting him with more force. I'm attracting Max with less force. As a result, if I'm pulling him, I'm going to be pulling Russell in harder, he'll be coming in closer. And so what causes the tides is the water on the side closer to the moon gets pulled harder and gets pulled away from the Earth. The water on the far side of the moon, that would be like Amelia, it's pulled even less, and so it kind of falls away from the Earth. So the water on the far side of the moon goes away from the Earth. The water on the near side of the moon gets pulled toward the moon and away from the Earth. So you have high tides on both of those two sides. That's what we call a tidal force. Well, with the moon isn't perfectly symmetric. And because it's not perfectly symmetric, you have like a chunk here, and as it comes around, that gets pulled more, and it's slowly altered the orbit of the moon until it's now stuck with one side always facing the Earth. And because that one side is actually always facing the Earth, the core of the moon has migrated toward that side as well. So the core of the moon is not at its center, it's actually pulled a little closer on the side facing the Earth. So when we look at the moon, we always see the same side of the moon. Now there is a little bit of jitter to this, because the orbit of the Earth is, or the moon around the Earth is not a perfect circle. Sometimes it's farther and it goes slower. Sometimes it's closer and it goes faster. And so because of that variation, it has just a little itty bit of wiggle like this. So the same side is facing the Earth, but it wiggles a little bit depending on where it is in its rotation. Really curious, I think. Even more curious when we get to Mercury. Mercury has a more eccentric orbit, and so it can't lock like the moon, and instead it's in a 3-to-2 resonance. For every 2 orbits, it does 3 rotations. I think I have that right. So, interesting tidal locking. But what was the important thing of what I said here? We have the moon is locked, so one side always faces the Earth. So when we look at the moon, it always looks pretty much the same. And we have a difference between the sidereal and synodic months, because the sidereal is the time for one complete orbit, but since the Earth is orbiting around the sun at the same time, and the full moon, actually we measure moons from new moon to new moon. The new moon occurs, if you look at the little picture, I'll zoom in on the picture. The new moon occurs when the moon is on the same side of the Earth as the sun. And so since the Earth goes through essentially 1/12 of an orbit in a month, then the moon has to do like another 12th of an orbit each month before it gets back to a new moon. So that's why there's a significant difference between the synodic and the sidereal months. So synodic is the one that's new moon to new moon. It's the longer of the two, which is why I was pretty sure I had a mistake here. And roughly 29.5. Sidereal is with respect to the stars, and the shorter one, 27.3. Lunar cycles. This graphic shows positions with the lunar cycle. Now notice I said the same side always faces the Earth. So this side, that red dot would be the same piece of the moon always facing the Earth.
Question.
Yes.
Could just be crazy, but I heard that.
Could be.
You know, I probably.
Go ahead.
I
Sorry.
would look at it. But I heard that the dark side of the moon, that we don't usually see, has significantly less craters than the.
Okay. The part Pink Floyd sings about, right? You will read some astronomy textbooks, and I think ours is one, that vehemently argues there is no such thing as the dark side of the moon. And it depends on your interpretation of the dark side of the moon if you even buy into it exists. So I will answer your question. I don't have pretty pictures of it now. We'll have pretty pictures of it later to see it. But as you see well, to answer his first question, yes, the other side of the moon looks very different as far as the craters. Much more craters on that side. Yeah. And we'll look at them later on in the semester. So that's the short answer. You're right. As far as the dark side of the moon, if you look at position number 1, which is a new moon, it's new moon because the side facing the Earth is completely in the shadow of the moon. Right? The moon's blocking all the sunlight, so the side we see is dark. So some people say, see, that's the dark side of the moon at that instant. The other side, the side that you reference as the dark side, is completely lit up at that time. And that's why many textbooks say there is no such thing as the dark side. I tend to say, well, at any time, half of it's light, half of it's dark, and the dark side just means the part that is dark at any time. In that definition, there is a dark side. It's not worth arguing about. It's just more fun to make jokes about Star Wars than anything else. So in position 1 there, the moon is lit up on the side you cannot see. It's a new moon. New moon means dark. Phase 2 there, if you look, the sun is still shining on half of the moon, but the half of the moon that it's shining on, here we couldn't see any of the part that's shining on. I'm doing a separation between the parts that are lit up and parts that aren't in green. And then in whatever you want to call this color, purple, I will mark what we see on Earth. I won't mark the two that they're the same. So if you're looking there, in position 2, you see that there's this little wedge here. It'll be blue. This little wedge that's lit up that we can see. But that's only a small part of the circle, and so we say that's a crescent. A crescent because it's just a little edge of the circle. Now, if you get to position 3, half of it is lit up. And so position 3 we call the first quarter because it's 1/4 of the way through the cycle, first quarter. Position 4, you see more than half. Position 5, it's completely filled. We could call that second quarter, but instead we call it full. Then we go 6, it's mostly lit up again. 7, it's half, and that's third quarter of the way through. 8 is another crescent, and then back to new. So that's our lunar cycle. Now, I did not name the intermediate ones. So the position 2 is a waxing crescent. Waxing means it's getting larger. Position 4, it's still waxing because it's still filling out. But now instead of being less than half, it's more than half, and we call that a gibbous, which means like humpbacked or pregnant. So it's not a full circle, but it's more than a half circle. Then, of course, position 5 is the full moon. And then we go back to a gibbous, but now it's getting less, so that's a waning gibbous. And position 8, the last one there, is a waning crescent. Now, the time sequence here is going like this. So we go through that cycle, of course, waxing to full to waning. And notice it all has to do with geometry, where the sun is and where the moon is. Do you have a question, Max?
Yes. So I'm assuming that the moon is not on the same, like the moon doesn't line up with the celestial equator, because if it did, then if it came behind the Earth, it would block the sun's light.
Very astute, and that's coming up later in the lecture.
Okay.
You're absolutely right. That's the question I was going to ask is why don't we have an eclipse every time?
Yeah.
That's why. Now, you'll notice that I put the word dog here. Dog is a way to allow you to go out and look at the moon and get an idea where we are in the lunar cycle. So, for the waxing stages, the right side of the moon is the side that's complete. The left side is partial. And so the letter D is to represent it's complete on the right side. Now, of course, how do you decide the right side? You decide the right side by making sure the moon is not behind you. You stand so the moon is in front of you. Because we're 40 degrees north of the equator and the moon falls pretty close to the ecliptic, it's about 5 degrees off. So the moon is going to be always south of us. So as long as you're in the northern hemisphere, you stand so the moon is in the southern sky, and if you see the right side completed, it's waxing. The O is just for full moon to remind you it's the separator. And then the G is for complete on the left side. If you look at it in the southern sky and it's complete on the left side, then the moon is waning. So dog is a nice little mnemonic. You can just look at the moon, and provided you're not doing this action, you match it up with those letters and you can tell right away if it's waxing or waning. Now, Carrie Wolf, more than a decade ago, she went down to Australia. She came back. She was like, I realized when you're in the southern hemisphere, instead of dog, it's God. Right? Because if you're south of 23.5 degrees south, then the moon is always north. So when you look at the moon, you're looking north, and it's reversed which side is which because you changed direction you're looking at it from. So this here is a northern hemisphere. Specific rule. Okay, more things about observing the moon. Notice the picture in the top there is what it's going to look like at sunset. If you see the moon in the sky during sunset, that's going to mean that the right side is filled. If the right side is filled, is it waxing or waning?
It's
D for dog. Waxing. So if you can see the moon in the sky at sunset, then it's a waxing phase. Conversely, bottom right, at dawn, if you see the moon in the sky at dawn, it's the left side that's complete. It's the waning phase. Now we're going to go out to observe the sky. God willing, it'll be clear tomorrow night. We'll always meet here for lab. And especially now because the sun won't have set yet, I will lecture for about an hour before we go out. But when we go out, I looked at the moon this morning when I went to the gym. And this morning when I went to the gym, the moon looked like that. So is that waxing or waning? Waning. What's going to happen next? What comes after a waning crescent? New moon. So we're really close to the new moon. Now, if the moon is in the sky at sunrise, it's not going to be in the sky at sunset. That's when it's good for us to observe the sky in the early evening. If the moon is in the sky, it makes it much lighter and we can't see the faint stars as well. So we like it when it is a waning moon, because that means that the moon won't be in the sky while we're out there in the early evening. Unless, of course, you like getting up at 4 a.m. to view the sky. Then you'd like to be waxing. Okay. So you can see actually it has the days in the cycle here. This is day 28. That's pretty much what the moon looked like. How long was the cycle? The synodic cycle? 29 and a half days. So if it looks like this, we've got, day and a half or so before it's a new moon. Maybe a day from now, a new moon. It's a fairly short sequence. We talk about our year. What about our months? What's the definition of a month? There's really not a good one. In theory, it should be from new moon to new moon. In practice, that's not what we do with our Western culture. There are some calendars, and we're going to see some, that do measure the months that way. Now, we say that there are 12 months in a year. Well, 365.2422 divided by 29.5. Who's got a calculator? Somebody? I've not done this calculation recently. So 365.2422, you just put 365, both runs here, divided by 29 and a half. How many does that give us?
About 12.37.
Okay, so about 12.4 months in a year if you were to go through lunar cycles. Well, that leads to some interesting things like usually there's only going to be one new moon per month, one full moon per month. Every now and then we might have two full moons in a month. If we have two full moons in a month, one of the two primary definitions for a blue moon is I think it's the second new moon in a month. Might be the first new moon in a month that has two new moons, or full moon. Wow, screwed that one up. Full moon. I think it's the second full moon in a month. Another definition is the third of the 4 full moons in a quarter that has 4 full moons. But what do they both have in common? They're somewhat rare because you have 12.4-ish lunar cycles in a year. So essentially every 2.5 years on average, you would have one of those roll around. That's what makes it rare, a blue moon. What's a blue moon? We have other things like the harvest moon, another full moon that occurs. I think it's the last full moon before the equinox, the autumnal equinox. There's lots of moons with different names. The fox moon, I don't know what that is. and I'm not going to worry about it either. Let's move on to eclipses, since I do have 12 minutes. Here is a picture of an eclipse looking at the surface of the Earth. See that curvature? It's because the Earth actually is... Okay. When you look at that, it's really kind of interesting. You have a dark spot there, a dark shadow on the Earth. What's casting that shadow? The moon. What kind of eclipse do you call this? There's only 2 answers, but...
Solar.
Okay, this is a solar eclipse. It does say there, solar eclipse, now doesn't it? It's a solar eclipse, which means that if you happen to be in this region right here, the sun is completely blocked out. How many people have experienced a solar eclipse? Okay, a few of us. How many people have experienced a complete solar eclipse? I've experienced a complete annular eclipse, but not a complete annular eclipse is when you actually have the moon is farther and doesn't fill out enough to block the sun completely, so you see a ring around it. When I went to get married, my wife and I drove from here to California to get married, and we stopped in Santa Fe so we could observe the annular eclipse. It was cloudy. Talk about discouraging. Well, I'm going to probably come back to this. August 21, 2017. For those of you with no memory at all, that's the first day of school next school year. The first...
I won't be here.
That's a shame. The first day of school next school year, there will be a total solar eclipse visible right here in Lincoln, Nebraska. Now, we are, if you zoom in here, we are right on the edge of where it's going to be total. It will be total here, but we're on the edge. if you go just like 15 miles, oh, that was a beautiful color contrast. If you go just like 15 miles down here, you'll have like a minute and a half of complete blocking of the sun. So we're going to try to do something. We'll probably just have glasses and have it here on campus because we can't take the whole school, you know. Okay, we're going to stop classes and everybody jump in your car. We're going to drive for half hour. Okay, no. But it will be pretty awesome for the first day of school next school year. Those of you who aren't going to be here, I'm sorry, man. Hopefully you'll be somewhere.
Well, we can have everybody go into a panic and think the world's ending.
Somewhere between here, up there, basically Portland area, a little south of Portland, maybe Eugene, down to here, and is that still Georgia, or is that, I think that's still Georgia. There's that path, and if you're anywhere in that path on August 21, you'll be able to see the total eclipse. But notice it's a narrow path. If you're outside the path, well, you'll see a partial eclipse.
What's the other path?
Okay, the other path, if you look down the bottom left, that's 2024, April 8, 2024. This is showing all of the eclipses from 2001 to 2025. All of the complete solar eclipses, I should clarify. It's not showing lunar eclipses, and it's not showing partial eclipses. Sorry, I didn't hear you. Yeah, where are you going to be? Where to find a job?
That's true, but if I don't find a job out here, I'll be in Massachusetts.
Yeah, that's not the best viewing location.
Hey, get a try.
Yeah. Well, it's going to pass far north of Massachusetts then. Anyhow, that's something that I'm really looking forward to. So let's come back here. What causes the eclipse? The eclipse occurs when the moon falls directly in line between the sun and the earth. And as Max said, well, the moon comes around once a month. We have a new moon when the moon is between the sun and the earth because the sun is lighting up the other side. So one would suspect then that every new moon we should have an eclipse. But Max already nailed the reason we don't. The moon in its orbit around the earth is tilted about 5 degrees from the ecliptic, which is the path that the earth is orbiting around the sun. So in order to have an eclipse, you have to have the moon crossing the ecliptic at the time that you have a new moon. So the time when the moon is crossing the ecliptic, they call that an eclipse season. Because if it's a new moon, then the moon is between the earth and the sun, and you'll have a solar eclipse. If it's a full moon, then the moon is on the opposite side from the sun, so we're seeing the side completely lit up. But if the moon is crossing that line, it's going to fall into the Earth's shadow. And so that would be a lunar eclipse. So the eclipse season can have both lunar eclipses and solar eclipses. And it's long enough that sometimes you'll have a lunar eclipse and 2 weeks later a solar eclipse or vice versa. So looking at the shadows, there are 2 regions we talk about in the shadows. The umbra, the shadow, and the penumbra, which is right next to the shadow. The penumbra is partial shadow. So if you look in this picture, and once again, let's zoom. If you look in this picture, we have this region that's in gray. That is in complete shadow. So that's marked here as umbra. And so that umbra, the complete shadow, is creating an eclipse just in that tiny region. But we have, got to zoom out a little so we can see, light from the sun, so light from the top part of the sun passes here. Light from the bottom part passes here. Everything between here and here is going to have at least one side of the sun is blocked. So that's going to be in partial shadow. And so that's that's penumbra, the region that's partial shadow. Now, if the moon was on the other side, the moon would easily fit inside the complete umbra. In fact, you can have a lunar eclipse last for very long periods of time because it takes a while for the moon to go into and out of that shadow. So lunar eclipses, the moon is just darkened. Where do you have to be on Earth to see the lunar eclipse? Has to be nighttime. If it's nighttime, you can see it if it's occurring. So half of the Earth is going to see the lunar eclipse. But you have to be just in the special position on Earth to see the solar eclipse. So seeing a solar eclipse is much more rare, especially seeing a complete total solar eclipse. Seeing a lunar eclipse, everyone can see it as long as it's nighttime when it's occurring. So we've already talked about this picture. The Saros cycle was discovered by I believe this is pronounced Chaldeans, which, were the wise men back in Daniel's day, right? And they determined that every 18 years, 11 days, and 8 hours, or every 223 lunar cycles, the same eclipse would occur again. But because of that 8 hours is conveniently enough 1/3 of the day. And so that eclipse reoccurs, but it reoccurs 1/3 of the way around the Earth. So if you go through 3 of those cycles, so 54 years and 34 days, give or take because of the, give or take the number of days a month, because it's that, depending on the leap year, it could be 1 or 2 days into a month. You have a repeat of the same eclipse at the same location. So this eclipse that's going to occur in 2017 on August 21 should reoccur in 54 years. So 2017 plus 54 is going to be 1 and 5 is 6. Carry the 1, 71. So in 2071, in August, approximately September 26th, there will be another total solar eclipse right here. That's what the Saros cycle tells you. Went through 3 Saros cycles to get back to the same location. If we only go forward 18 years, 11 days, and 8 hours, it will reoccur, but it will reoccur shifted over 1/3 of the way through the Earth. So instead of being here, well, that's not the same one, but it looks like the same one, doesn't it? Right? That looks like it, but it's not. Actually, 18 years, right? That's not 18 going from 6 to 17. But it'll be very similar to that one there. So the Saros cycle is a cycle of repeating eclipses. How is it possible to have this nice, clean cycle? Well, it's because of that tilt that we talked about. I'm going to jump to this picture here that shows the tilt. So we have about a 5-degree tilt, 5 degrees right there, between the moon's orbit around the Earth and the Earth's orbit around the sun. And so it's an integer number of months because it's on a monthly cycle when it crosses the ecliptic. Most of the time we don't have eclipses because the Earth's shadow goes either above or below the moon. The moon's shadow goes either above or below Earth. So that's why we usually don't have them. What lunar phase is it when it's a solar eclipse? When the moon is blocking the sun, what phase is it going to be? New moon. What phase is it when we have a lunar eclipse? It's a full moon. Now, how many people have seen the movie Apocalypto? Not many. Well, in Apocalypto, the whole thing starts with the Incas? Or maybe it's the Aztecs. They're gathering up the jungle people and sacrificing them to their god because there is a solar eclipse. Now, we at least believe that ancient cultures, that the people who are educated knew well about eclipses, and they could predict them. They knew they'd come, they knew they would go. But they used these to control people for power. And they said things like, oh no, our God is angry, and he is taking away our son. He's eating our son, and we have to appease him. And so in that movie, they were appeasing their God by chopping off the heads of all these people until the eclipse goes away. The sun reemerges. Hooray! Everybody's free, right? Well, except for Apocalypto, instead of freeing them, they said, let's have some sport with them. And so they have them run and they're trying to kill them, just shooting them with the bows and arrows and stuff. And so one of these guys, our hero, he gets away and he's being chased. And that night, it's a full moon. And that's about the time I'm the kind of person, I'm in the theater watching a movie and I start laughing. Because if it was a solar eclipse, what phase the moon have to be? New moon. That night, how was it a full moon? But Mel Gibson apparently didn't hire scientists to help him out with this. Or maybe he knew and figured, I want the guy to be able to see what he's running at night. And if it's a new moon, he won't be able to see where he's running. By the way, you guys know Mel Gibson is coming out with a new movie, The Hacksaw Ridge, that should be really fun to watch, about a conscientious objector who refused to pick up a gun. We're out of time, so we'll stop there.